Hello. Howdy. So in this stream, I don't have the Altair. The Altair is elsewhere, but in this stream, I will just do some code stuff. So there's a couple things on the agenda tonight. So here for Logic Sim, I brought it into work and I showed it off. However, there are a couple things. So if a couple bugs that rear their head. So first of all, if I go here, I need to change this from 10 to 9 because there are 10 devices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, there are 9 devices, not 10 devices. And of course, this code right here is completely redundant, so I can just get rid of that. There was a couple of bugs. One bug was, yeah, so like basically what would happen is if you, oh my god, I hate this stupid autofocus. If you basically selected something, like if you had a signal and then you wanted to change that signal's value from low to high or high to low without resetting it as a signal, it would then change to a wire. So in order to fix that, I had to change that right there from a 10 to a 9. It was an off by 1 error thing. Then the other thing I want to do is I want to add a load and save really quick. Luckily, I asked Gemini that. Gemini's been pretty good lately. Let me just see what it does. Basically, look. Obviously, this is kind of what I think should have been is that I need a more human readable format, because basically what I'm doing is I was saving it as pure bytes, and that makes sense. That's the easiest way to do it technically, but for some reason it just was not working. So I need to do this instead. So let me see if I can copy and paste this. Save and load. Okay. So open up a file name as write only. Okay, that makes sense. And then, of course, if file goes null, error, file is not available. Makes sense. Okay. That makes sense. Then basically I want to printf file devices with the numdev. That makes sense. So okay, that makes sense. Then I want to print okay, let's look through this. So for I equals 0, and I, let's see, device type, device X, device Y, device value, device indev, device indev1, and output. That makes sense. I can do that. That makes total sense. Then connections. Okay. That makes sense. And then the connections will be saved as connections will be saved as connection source dev, target device, and input. And then of course fclose file. Now that all makes sense. Now I'm going to go up to the stretch and just make sure that looks about right. And if I recall, fprintf is just writing to a file. You're not doing fwrite, so it's not. Maybe fwrite was the problem. Maybe fwrite was the problem. Okay, that looks all correct. Now let's look at load. I'm just copying and pasting because like this is such a like I'm just copying and pasting this code. Load function. Let's see if this works. Lordy. Okay. Okay, so first, let us load file. Device is a double pointer, connections is a double pointer, and num-connections is a pointer. These will be changed to pointers inside the code here. So open it as a read-only file, and p_error, I think I can just change p_error to I think I can just set it to just return 1 because I don't care essentially. I do care, I just don't care enough to set error checking correctly. Basically I'd have to pass in the terminal into the load and save functions, and I just don't want to right now, but I will. I will need to. Okay. Read in the number of devices. So let's see how I end up parsing things. Okay, let me just, there we go. If, oh, hang on, let me, know what? Let me pass in. Let me pass in the terminal really quick. Where is my cursor? So in this case, I will do term t put s. I really wish I could just do put s, but apparently I can't. I can't do just put s because put s will override put s. If I don't have stdio or stdlib in there, if I don't have stdlib included, or stdio included, sorry, it would just work fine, but unfortunately I can't. So, yeah. Let me just see, how do I call it? And then okay. That looks right. Okay. That looks right. Okay. So the reading number of devices. So if scanf string number and string comp. String comp I don't think exists in here. Where is this? Oh, this is that. Okay. Right. One moment. Okay. Looks about right. Okay. Structure member name was expected here. Oh, right. Okay. I guess string compare is part of the C standard library. That's pretty cool. I didn't know that. I mean, obviously I knew that. I just could have sworn that it wasn't part of the C standard library for CP/M. Okay. So we read the number of devices. We will allocate memory for devices. So we have devices equals device malloc if devices not equal null, free devices. I think this is correct. Free if already pointing to something. Okay. This is okay, I think. Then devices equals device malloc number of devices numdev numdev. There. Okay, we're just making sure that this is working. And then term t_s term fclose file. So after we have allocated the memory for the devices, we will read the device data. Okay. Okay, now let's clean this up. So of course remove this, and then remove this because that's a pointer. I just need to know numdev now. If scanf file and devices, nope, there we go. I type devices I x y x y is not equal 7. So does fscanf just return the number of things you have successfully converted? Let's look that up really quick. Fscanf man. And upon successful completion, these functions shall return the number of successfully matched and assigned input items. Okay, that's pretty helpful. It won't tell you which one, I don't think. This number can be 0 if, in the event of an early matching failure, if the input ends before the first conversion of any, an EOF shall be returned if an error occurs before the first conversion. Shall be returned, error notice shall be set to indicate error if the read error occurs. Okay, so basically it'll fail and return which one it failed on. So that's pretty helpful. Okay. Then term t put s. Isn't it pretty awesome just being able to just port your stuff like so easily when you have an object-oriented C library. Free devices, fclose file, and then devices shape equals shape table devices I dot type, and it's there right there for me. Read data. Okay, I think we are getting somewhere. Then next we will read number of connections. Okay. Okay. If f skin of file, string buffer, name, and then of course address of connection does not equal 2, string compare buffer connections does not equal buffer connections, then term s term for devices, that looks all correct. So then after number of connections, allocate the memory for the connections. Okay. So connections equals connection malloc number connections. So again, numconnects needs to be changed to not a pointer. This needs to change to term t put s. Term, of course, I could always change it to an error, but I really don't care. The error, p error, and all that actually carries a little bit more weight. STD error. There are other files on CP/M. I think STD error does exist, but it's so much hassle to set that up. It's not probably not hassle to set it up. It's just I don't know how to set it up, and I probably don't need to set it up. So we're not going to deal with that. Anyway, I'm going to copy this, because I think that's something I need. If basically if there's any connections, just wipe them first, because if you do malloc on an already malloc thing, I can't imagine good things would happen. And now read connection data. Okay. After this, we're gonna do some cool assembly stuff, which we haven't done in a while. So let's change this. We're going to delete that. Clean up the end here. If scan file 1, 2, 3, and connection, source input, and source trigger device, source input radius angle 3. Then term t put s, term, cool, free devices for connections, close file. Cool. Let me close. Let me go here. Okay. And main. Oh, here's cool. So basically I go to this down here. So basically if load circuit fails, basically just do it myself. That's pretty cool. And we're just gonna have circuit CRT. And then we're going to save the circuit. I need to pass in gterm. Okay. Circuit devices dev I will delete. Connections I will delete. Dev I will delete. And connections I will delete. Okay, now let's try building it. Oh, right. We go up here. Okay. Looks good. T put S. What? What? Why is T put S not defined? So stream is on. Yeah. Sorry. Yeah, I pinged you. That's. Bro got a haircut. Dog, I've had a haircut. What are you talking about? Okay, why is it saying T put S is undefined? Oh, here. That's why. You can subtract functions? Oh, that's terrible. That's terrible. You can subtract functions with Aztec C? I don't ever never know why you would ever do that. You gotta make it blue. What the? Hang on. Oh, come on. Really? My God, I swear, I did the at sign. My God, I am a special boy. Technically, in my Lua runtime, you can subtract functions and tables to become -2. Why do you have that? So supposedly it builds, but it's 23.875 bytes now instead of 16. It must be fscanf. Fscanf must be just so huge, and fwrite or whatever it was probably much later. Ugh. Well, that's a shame. If I needed to, well, I guess 23 kilobytes. It's not terrible. Dynamic types are great. Yeah, man. I guess if I need to make my own file saving routine, I can. I just don't want to be bothered. Well, I built it. Okay, now on to the next thing for tonight. Basically, what is type safety, Doug? Basically, a coworker today was on the front panel on the Altair, and what he wanted to do was he wanted to do this. Let's see, sample. Let me save this as an assembly file as front panel.asm. Basically, user defined assembly 8080. So what I'm trying to make here is on the Altair 8800 front panel. I'll show you here. On the Altair, there are lights, okay? And this is actually a fantastic example because this is exactly what I want to do. Notice how there's a row of lights up here and there's a longer row of lights down here. Don't worry about these ones. Now, the thing you need to know about these lights is that they are wired directly into the CPU. These are status flags. Like you see status flags on the, yeah, right? Yeah, recognize on YouTube Shorts, yeah. So the lights up here, and I use this a ton. The lights up here and here are for status flags. Like, is the CPU in a wait state? Is it in an interrupt mode? Is it going to read from memory? Is it going to write to memory? Is it using the data bus? Is it using the address bus? That sort of thing. That's what those lights are for. These lights here are the data LEDs, and these lights down here are all the address LEDs. So when the CPU reads from memory, whether it be for an instruction fetch, whether it be for you're telling it to read data or whatever, it will light up exactly which address it's reading from because it's connected, those LEDs are connected to the address lines. And there's 16 address lines because it's a chip with 16 address lines. It can access up to 64K of RAM. And there's 8 data bits because it's an 8-bit chip. Each location, sorry about that. Each location in RAM holds 1 byte. It's an 8-bit chip. So at this location holds this byte is basically how you read the front panel. What my coworker wanted to do, he wanted to see if he could display a binary number on the front panel, and very quickly he realized he couldn't. You can't do that with the Altair 8800, because the front panel has no port for it. You can't write out a number to it. Hey, look, there's my hand. If you use this computer, the IMSIA, this actually has a completely separate 8-bit data port where you can write 8-bit numbers to. But yeah, where was it? This one you can't. But you can, because look at these numbers. Look at this part of the address. The left half of the address is going down like blinking lights. Because what happens is if you slam memory over and over, you keep hitting those lights over and over, and through persistence of vision, it looks like you're displaying an LED. So if you take a register with your 8-bit value, put it into the high byte of the HL register into H, and then you access that memory for like 8 times in a row, and then you loop that for like 100 times, exactly DESP. So you slam memory to display the number. The number will actually, instead of being in data, it will be part of an address. And because your program will occupy the lower part of the program, it will never reach the higher parts of the RAM. You don't have to worry about your code leaking into these lower parts of the high byte. That's exactly correct. So your program can only be like 256 bytes long, but that's long enough. This is the best way to store binary numbers. Yes, this is like the most trashy way to display numbers. And this is partially why the Altair 8800 never took off. It took off, but it didn't take off like the Apple did, or it didn't take off like the Kim 1, because as a bare bones kit, it kind of fucking sucked. You couldn't do much with it. You can toggle in your program, but if you don't have an input-output device, like at least a paper tape or at least a terminal, yeah, storing them, no, exactly, man. Yeah, no, it is the most trashy way to store them. But if you didn't have an input-output device of any sort, and you just had the LEDs, the next best thing is you could have an AM radio. You could have an AM radio sitting on top of your Altair. If you turned it to static, you could listen to it while it was working, and the certain interference of you accessing certain things would change the pitch. In fact, you could play music that way. So the first I/O device for the Altair was actually a speaker. Anyway, I want to make a routine for my coworker that I can put a number in register A and then display it in the leftmost address bits. Well, how are we going to do that? Well, funny you should ask. One moment. This right here is the Altair 8800 1.4 manual. Yo, Restream. And if you look at this manual, which tells you how to assemble a kit, how to boot hard drives and stuff, and my crappy Promised Neverland inspired Japanese drawings, you will find source code for the Kill the Bit program. I'm going to go all the way in the back. You go all the way in the back. Moment. You go all the way in the back. Here. This here is the Kill the Bit source code. And it actually has the entire source code and listing. It has the source code and it has the exact byte listing for you to punch in how to do it. And the reason I Kill the Bit, because Kill the Bit actually does exactly what I want this to do. let me read it off to you. So first what you do is you load the HL to 0. Let me just type this out for you here. Sample routine takes number. Let me make this bigger for you guys. There you go. In register A, displays it on the leftmost 8 LEDs of the address lights. Okay, so first, org 100H, as always, start. So the first thing, it says, oh sorry, instead of 100H, we're going to do 0H because we want to keep it in the low part of the RAM. We don't want it in the high part of the RAM. So start LXI-H0. So load HL to 0. Then it says to NVID 080H. NVID 080H. Load DE to initial value. So I'm first writing kill the bit, and then I'm going to go in and make it my routine. And this is insert accumulator here. Okay, that's what we're going to do. Then it says LXIB0EH. LXIB0EH. Higher value means faster. I will show you what this does later, and it's just kind of a fucking nightmare. This is not how I would increment through a loop, especially on the front panel. To me, this is just too much work. But maybe they have something, maybe they know something else that I don't know. So B will be your delay. Here we go. It says beginning. You know what? We can change this to loop. Okay. So then it says LDAX D slam address at DE. Okay. 1, 2, 3, 4. It says I want to do this 4 times. So I want to access the memory location at DE 4 times. Okay. Then I need to double add B. Add BC to HL, store to HL. So this is an accumulate. Then I will J and C, jump if not carry, to loop. And then continue on your code. So then the rest of kill the bit is grabbing your input, exclusive ORing it, rotating it, move it to D, and then jump to the beginning. So basically what that is okay, Desp, I'll see you in a bit. Basically what that does is it grabs your input that you have hit the switch on. Seriously. It grabs the input that you've hit the switch on, and then whatever, it'll XOR that against your current address. Because when you kill the bit, when you hit an LED that's off, it'll turn it on. If you hit the LED on, it'll turn it off. And the whole point is to turn all the LEDs off. So let me change this to disp routine and then routine loop. So we are going to LXI D0, load DE to 0, move DA, AB, move DA, move accumulator to high byte of DE. Okay. So this is the routine. Routine to display accumulator at on high byte of addresses of address LEDs. Okay, so then you return. Push PSW, pop PSW, preserve accumulator and flags, back up accumulator and flags. Okay, so basically what he wants to do is he wants to do something like load immediate MVI A42, load 42 to accumulator, call disp routine, call display routine, halt. Do I not have halt? There we go. Halt. Halt CPU. And then here, well, you know what, here, let me move this over so you guys can see all the comments. Jump, if not overflowed. So basically, this is the delay, and that means a higher value will make the overflow happen sooner. So let's actually do something like, if you did like 01, you would see it even sooner. Let me check my book here just to make sure. Yeah. Yep. Okay, we're good. So let us assemble this for my coworker. So 0, 0, 0, 0, 1, 0, 0, 2, 0, 0, 3, 0. Okay, so let us move it here. Okay. let us do something like alter 8080 instructions at text. What? There we go. So what's going on? Okay, so let's hand assemble this. So MVI A42. MVI is going to be 0, 0, 1, 1, 1, 1, 1, 0. That's 1, 2, 3, 4. Yep. And then 42. Calculator. 42. Binary is going to be 0, 0, 1, 0, 1, 0, 1, 0. Okay. So let us break this apart. This will become 0. Basically, I know what this is because the first opcode, MVI, is 0, 0, and then DDD is destination register. And because I want to do the destination of A, and I know A is 1, 1, 1, so it's 0, 0, 1, 1, 1, 1, 0. So 1, 1, 1 becomes 7, and then 1, 1, 0 becomes 6. So MVI A is 076. And of course you got to separate this out, so it becomes 0, 5, 2. Okay, so we have the first byte done, and remember that 10 in octal is 8, so we'll have 8 bytes across, and then before we'll go to the next one. So call display routine. So if we go down to call is 1, 1, 0, 0, 1, 1, 0, 1. So this is going to be 3, 1, 5, and then the display routine we'll do XXX because I don't know what the display routine address is right yet, but we will. 1, 2, 3, 4, 5. Okay. And then halt. And halt is 0, 1, 1, 1, 0, 1, 1, 0. So this becomes 1. This becomes 5, 6. This becomes 6. Okay. 1, 2, 3, 4, 5, 6. And you have 2 more bytes to work with. So push PSW. So push is going to be 1, 1 register pair 0, 1, 0, 1. And the register pair for PSW is going to be, so for push pop you can't push stack pointers onto the stack because that wouldn't make any sense. I mean you can, but you can't push the stack onto the stack directly. So it will be 1, 1, 0, 1, 0, 1. Yep. So then let's group that up. So that's 3. That is 6. That is 5. 1, 2, 3, 4, 5, 6, 7. And then we will do one more, 8. So push PSW and then LXIH0. LXI register pair. So 0, 0. And the register pair HL is going to be 0, 1. And then 0, 0, 0, 1. Hey Desp, as you can see, I have my routine written, and now I'm hand assembling it for my coworker for him to punch in tomorrow. So 0, 2, 1. And then, of course, I next need to do the low byte and high byte. So that becomes 0, 0, 0, 0, 0, 0. And then I will go here and do load immediate for D, E, which is 01, and then 0, 0, 0, 1. Let's change this again. 0, 0, 0, 0, 0, 0, 0, 1. Opcode here is going to be 0, 0, 1. And the opcode here is going to be 0, 2, 1. And then 0, 0, 0, 0, 0, 0. Load it to 0 again. Okay. And then we have a move DA. And move is 0, 1, register pair, destination to D. So that's 0, 1, 0, 1, 1, 1. Because 1, 1, 1 I think is 0, yep. Yep. So this becomes 7. This becomes 2. And that becomes 1. Okay. And then LXI B 0E. So basically I'm loading BC with 0, 0, 0E. Let's do that. So LXI again is 0, 0, register pair, BC. Bro, I just remembered I saw this video of a guy that ran Doom with the TypeScript. God damn it. Of course, man, of course. Register pair BC is going to be 0, 0. Wait, what? And then 0, 0, 0, 1. Hang on, the first one is H. HL is 1, 0. 0, 0, 1, 0, 1, 2, 3, 1. 4, 1, 0. There we go. That's more like it. 0, 0, 0, 1 is BC. And then low byte first, so that's 0E. And E is octal 16. Okay, so we just did LXIBOE using only types, not even code. It's a whole ass WebAssembly emulator. Jesus. Dude, some people have free time. You know, I think I have a ton of free time, but Jesus. Then we load accumulator from address D. So LDAX RP. So we're going to do 0, 0, and then D is going to be 0, 1, and then it's going to be 1, 0, 1, 0, which is going to be 0, 3, 2. And then we run that 1, 2, 3, 4 times. 1, 2, 3, 4. And then we do a double add B. Double add is going to be 0, 0. B is going to be, BC is going to be 0, 0. Double add 0. No. Yeah. Double add. Yep, okay, makes sense. Double add 0, then 1, 0, 0, 1. It's going to be 0. It's going to be 1, 1. And then it's just that. And then jump, not carry, return loop. Okay, we're almost done, we're almost done. So jump is going to be 1, 1. And the carry code 010. Not carry is going to be 010. And then jump 010. So it's going to be 3, 2, 2. And then AAA, YY, BBB. Okay, because that's for the return loop. We will figure that out. Pop PSW. So 1, 1, and then the return code for that is 1, 1, 0, 0, 0, 1. So this is going to be 3, 6, 1. Okay. And then return. One, 1, 0, 0, 1, 0, 0, 1. So it's going to be 3, 1, 1. Okay. Almost done here. Almost done. So display routine is going to be after the halt. So this will be the first byte of it. So the byte location will be the byte location will be 0, 0, 0, then 0, 1, 2, 3, 4, 5, 6. 0, 0, okay. Low byte first. High byte next. Okay. And then return loop is the LDAX. So we got 8, 16, we got 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 17 is going to be 0, 0, 0, 0, 17, and then 17 in hex is going to be 0, 2, 1. So this will be low byte. This will be high byte. Okay, and I think, let me look through just to make sure, and I think that this code will be ready for my coworker tomorrow, for him to punch in and then to use as he wants. Displaying will last as long as displaying time, display time will be determined by register BC. And it should last for a bit. It's like oh, I can see that. Like you can see it. It's if you want to increase it, you can definitely lower it. You can lower this number. Okay, let's look through. MVI A42. A is 111. So MVI 001 sorry 00 1117 1106. Yep. Okay. Call. I'm gonna go down to call. Call is 11, which is 3, 001, which is 1, 3, 1, 5. Sorry, 315. This here is byte 42. Yep. Then 6, 0, 0, and then halt. Halt is 1, 110, 110, 166. Yep. And the next one is push. PSW. PSW is 11. Yep. Push is going to be 3, 6, 5. That's correct. 3, 6, 5. LXI-H0. So LXI-H is going to be register pair. H is going to be HL10. So it should be 0, 2, 1. 0, 2, 1. H L so 2, 1, 0. Nope. 4 was correct. What are we working on? So light fire. Yeah. Here's from. This is it's kind of esoteric, but I am working on an assembly language program for a coworker who was very fascinated by my Altair, and the Altair is what the hell? There we go. This thing. It is this computer. He was very fascinated by this computer. It uses a bunch of lights as the default output device. You have your address lights, which show which address you're at, and the data, which is what data is on that, is in that address location. You can't write a number directly to the lights to show. I can't write a binary number to the lights. It just doesn't have the capability. Yeah, you've seen this before, yeah. In order to display a number on the lights, you have to do like the most convoluted stuff of taking that number and turning it into an address, and then accessing that address many, many, many times, because whenever you access an address, the lights come on. So if you put that number into an address, part of the address that is not part of your code, and you access it many times, it is going to be a clear, somewhat dim, but a clear LED mark of what your value is. So basically I have a number being moved into the accumulator, calling this routine, and then halting the program, just so I can have the guy punch it in and see that there is a way to debug, there is a way to flash contents of the register. It's just going to be kind of esoteric and kind of a bitch. And what I'm doing right now is I'm taking this code and putting it into machine code, into the literal numbers that your computer will run physically to run this. And this isn't a computer that you have. This is the Altair, so it's a little bit older. So anyway, I finished hand assembling the first line. Let's check the next line. I want to load 00 So 0, 0, yep. And then 0, 1 should be register pair DE. Yep, that's correct. And then load 0, 0. Yep, that's correct. And then after that, I want to move A to D. So move is 0, 1. Yep, that's correct. And destination should be 7. No, sorry, D is 0, 1, 0, which is 2, that's correct. And then 7 is A, so move A. Literally, here is the opcode family, here is the source, and here is the destination in the middle. So that's kind of easy to see. Whenever you see a 1 on the front, you know that's a move. Kind of. When you wait, what is the call? Hang on. I think it's because there's no register 110. Move. Hang on, what? Hang on, I'm losing my mind. If I moved M to M, I would get the same opcode as halt. That's interesting. You would never use move MM, but you could. Wild. That is wild. I've never. Okay. That's a quirk of the instruction set. Anyway, that's good. Move the A, LXI, B, O, E, so B, LXI, load B, register pair, BC should be 0, 0, 1, so, yep, 0, 0, 1, and then low byte, high byte, this should be hex E, and this, yep, and then LDAXD, load accumulator from register pair. D is going to be DE, which is going to be 01. So 0, 0, so 0, 3, 2, 1, 2, 3, 4 times. That's correct. And then double add B. B should be 0, 0. BC00 double add 0, 1, 1, yep, and then jump not carry. So jump starts with 1, 1 should be 3, yep, and not carry should be 0, 1, 0. Zero, 1, 0 is 2 and 2, yep, 3, 2, 2, and then 21 is 17, which is right here. That's correct. And then 3, 6 to 1 should be pop. PSW should be flag 1, 1, which is correct. Waiting for pitch pop. So PSW push 3, 6, 5. Alright, pop. 3, 6, 1, yes, yes. Pop, yes. and then return. And return should just be 311. Okay, we have it hand assembled. It is hand assembled, it is correct. And cool. I have it ready for my coworker, and he can now punch this in and display numbers using the front panel. It is the most convoluted way. It's a bitch, but it's very doable. And just remember that this isn't generally something you would hand program yourself. But if you had no other way to program this machine, this is how you would do it. Trying to think, did I need to do anything else tonight? This is some Boon Pro. I haven't done any learning today, so let's do it. That is my younger brother. Sorry. Oh, far away. Sorry, go. What's that? Sorry. Well, Nani? Moscow. Hand spinner だよ。Okay? あなたはミクのお父さんですか? Your father? It's break time now, so おやすみ. So 今からおやすみの時間です. Okay, this is my pen. So これも私のペンです。私は誰かが家を出るときに必ずいってらっしゃいという。Okay? 弟手伝うつもりなの? So you're planning to help your brother. Tsumori desu is I expect to, right? 息子? Hi. 優しいね. So hey, you're nice, right? So hi. Or use more formal. Use more formal. What is more formal than hi? This is the part that I don't like about Boon Pro. It's not very straightforward on like what they actually expect. Hi. So this. What? I guess. Sure. I'll go with that. Buka. Shiro. Copy shimashita. And then your boss. Jusho. Arigatou gozaimasu. Arigatou gozaimasu. Right, it's your boss, so he'll just say probably arigato instead. Minagara. Looking at the picture, this is my father. Kore wa watashi no chichi desu. Okay. And then, Buka ga joshi ni subordinate the boss. もう一回言ってごめんなさい. Is there more? ありがとうございます. Yeah, I'm not. ごめんなさいお願いします. すみません. I beg your pardon. すみません. Really? Okay. すみません high school student, so high school student の時は大学受験のためにたくさん勉強しました. Right, I did a lot of studying and exams for university institute exams. So basically, ko is high school, and then Nensei is school age student. So say, I think, yes, kokosei is high school student. Jizo's expression look very gentle. I think a Jizo is a Buddhist deity. I'm not really sure. I don't understand why they place so much emphasis on learning this. Oh, Jizo-san. 顔はとっても優しいです。優しい。あなたの little brother 弟は何歳なの? How old is your little brother, right? Angie, okay, そのからお小遣いをもらった。先生? そうですね。そうですね。羨ましいです。羨ましい。Let's try a different particle here. そうですか. Right, そうですか. You say thank you for the meal after eating. ごちそうさま。ごちそうさまというのは食べ終わった後です. So after finishing the meal, after finishing eating, you say ごちそうさま. New shine, new employee. この下さんって誰ですか? Which one, right? Who is this person? Okay. I'm not quite a beginner in Japanese. I'm actually quite intermediate. I just had to completely restart studying because I hit a wall so hard and didn't study for so long. I could not progress anymore. So I'm just my knowledge is much higher than this, but this forces me to slow down and actually understand this. 私の妹は8歳です。She's 8 years old. 9 a.m. 午前9時です。午前9時です。9時午前. I've heard it both ways. In Genki, the Genki textbook, it actually just goes in afterward. 今、おはようって言ったのは誰? おはよう. Okay. Cool. Let us just learn a couple here. Dare. Sorry, dore is which. Dare is who. This is kono. Sono. Right. Ono is over there. And dono is which way, right? Koko is here. Soko is here. Asoko is over there. Doko is where. And then who is dare. Let's try the review. So which one is your book? Dochi. That's not, Doko? Oh my god, I'm gonna, come on, I know this one. I just immediately say dochira. Dochira, I don't know. God damn it. Dore. Dore desu ka? I knew that. God damn it. この漢字は何と読みますか? How's this kanji read? 読みますか? Right, okay, not 話します or whatever. So that day, 日は雨でした. Soko? その、あの日, right? あの日. That house is mine. あの 家は私の家です. It could be sono. Maybe sono is this. I don't know. It's pretty ambiguous when using Bunpro. あなたは which color? どちら色が好きです? I would actually say that, but I keep is don't know. I knew that. Don't know because it's a I should hit enter. It's a noun. This here, Toto. Wahaha, no, heiya desu. This is my mother's room. Isoire, sorry, hurry. Nikimasu is to go. So there is, so, go. Watashi wa live over there. Watashi wa Soto ni sunde iru. Okay. There. Doko ni ikitai, where do you want to go? Who are you? Anata wa doko? Which one is my book? Dore desu ka? Anata no, right? And then anata wa, who are you? My god. Dare? Dare? Cool. Turn to dashboard. I suppose I have time to do another set of 10 and then I will head off. Oishi, yep, makes sense. Sakana, tonkatsu, yep. Niki, menu, yasai, vegetable, yep. And pizza, pencil, yep. Casa, umbrella, parasol, that's also a pretty cute kanji. Kaban is right. Kutsu is shoes. And let us review. These are pretty easy. Oishi. このケーキは美味しいです。私は魚が好きだ。トンカツを食べる。そう、腹に肉がたくさんつく。So,肉 getting a lot of meat in my stomach. Well, brother, that's abra. That's fat. Restaurant no menu or meter. Show info. Just menu. Okay. Yeah, site. And pizza. Umbrella. Casa. Tojiru. そのカバンは誰のもの whose bag does this belong to? Shoes. Kitsu. Haku, to put on. So to put on clothes, imagine typing like this. You can actually switch keyboards. So, Desp, really quick. I'm typing the phonetic alphabet, so it's really easy. Japanese uses a single consonant and a single vowel. That's it. That's you only have. That's how all the syllables work: a single consonant, single vowel. Then you can have vowels a, e, a, o, u. But beyond that, it's just that. There is one single consonant syllable. So like konnichiwa, right? We say, oh, konnichiwa, but actually it's konnichi, so konnichiwa, that sort of thing. But yeah, I type in the phonetic alphabet, and then this will just automatically switch it to the kanji that I need, because it is kind of a nightmare to like type it and then scroll through which kanji you need. It's just a bitch. Restaurant no menu. Okay. Let's do another one because those words are pretty easy and I pretty much know them anyway. Saihu is wallet. Okay, this is the last one. After this one, I'm headed to bed. Jisho is dictionary. Okay. Jitensha is bicycle. Shinbun is newspaper. T-shatsu is t-shirt. Toke is watch or clock, right? And then noto, notebook. Pen, hat is boshi. Yep. Book is hon. And let's do this. So wallet. Saihu. Dictionaries is Jisho. No, it was Jisho, not Jisho. I want this bike. Jitensha. Newspaper Shinbun. Okay, t-shirt T-shatsu. T-shatsu. Oh, okay, I think what it's saying is I have to do T-shatsu. What? No, oh, shatsu, it's already there, my god. This watch belongs to him, okay. This noto, pen, hat, boshi, book, hon, dictionaries, jisho. Okay, there we go. Yeah, I already know these words. These are words that you just, you know, they're the most basic. You know what? I lied. Let me do one more. Come on, man. I gotta get this goddamn book finished. I'm supposed to be like intermediate Japanese. I don't need to be fucking around this book. Okay, last one. I swear. Last one at the bed. Okay. Kisaten is coffee shop. Yep. Ginko is bank. Toire is bathroom. Yep. Toshokan is library. Computer. So yeah, basically if you need to say a word in Japanese, just say it super fucking racist and you probably got it right, because computer. Ikura desu, how much, right? In is the yen, and takai is high, taube also expensive. Irashaimase is welcome. It's a shortened form of some super polite phrase. I don't know, it's like some thing. People fall into a trap of trying to dive into the nitty gritty very early on. I mean, like within weeks of like learning Japanese. Like, oh, I know all this esoteric shit about the language. You don't need to know it. Onegai shimasu. Irashaimase. Okay. Onegai shimasu is please, right? Okay, let's do this. Let's try this. So, Kisaten, bank, ginko, a bathroom, toire, a library, toshokan. I don't think. Toshokan, just no ooze. Yes. Computer. How much? Ikura. Oh, I spelled it wrong. Circle N. Kyoku. Yureberu. Gatakai. Welcome. Irashaimase. please sign onegai shimasu. Library Toshokan. How much? Ikura. There we go. Okay. Now I'm done. Okay, guys. So I will transfer this file over here to my phone so I can bring it to my coworker tomorrow. And then I will, stream again. I don't know when. Probably later this week. Probably Friday. Probably tomorrow or Friday. And yeah, I will see you then.